So this is, part two of, of the result on the impossibility on embedding triangle-rich graphs in low-dimensional through low-dimensional embeddings. And today I will actually go over the details of the proof. For as long as I hope that I will not require the entire hour. I will try to give as much detail as possible without, sort of getting into a lot of the nitty-gritties of the specific calculations. So recall, so basically, here's the theorem that I want to prove. So
are you recording this?
I am recording it. Yes.
Thank you.
Yeah, so I'm recording it and I'll put it on YouTube as before. I'm just not using Zoom to record. Yeah. Okay, so recall that, the way that we have a setup is that we have this collection of vectors v1, v2, up to vn in R to the d, and these are going to be the vectors that represent the vertices. So we will use this. So the graph model that these vectors will create is as follows. So I'll say the probability that ij is an edge is going to be set to, essentially I want to set it to the dot product. So I want to set it to vi dot vj, to the dot product. And of course the problem is that this dot product might not be in 0 or 1. And therefore what I would do is, I would basically take the min of these values, but also take the max over there. So in other words, just to sort of pictorially show you what's going on, if I plot the value of vi dot vj here, and this is the probability of an edge, if it's negative, I set it to be 0. Between 0 and 1, I basically set it to be equal to the value, and then after that I cap it off at 1. You could imagine smoother versions of this, but this is what we will have for the theorem. And then G, the graph G is generated by independently generating edges for all pairs of vertices. Now, a minor comment that you might have is that this seems like it's potentially. Again, this is the model that is typically assumed by many of the results. But even let's just think about implementing such a model. You might think that this is too expensive because you have to do it for all pairs. And given that the graph you generate, the graphs that people care about, are typically sparse, there are more efficient ways of generating these edges, at the cost of maybe a little bit mild dependence between the edges. But this is not that important. Again, given these vectors, this is the graph model that we will construct. And remember that the property, sort of the key property of social networks, is we were saying that there are omega n triangles incident to constant degree vertices. And so specifically, sort of in the paper, there were two parameters used for this. And because because I want to talk about the model specifically, and in the model the degrees itself are random variables, I'm going to sort of frame things in terms of expected degree. So I'll say that with respect to the model, So think of, I will use these constants just to describe what I'm doing, but in the calculations I'll just say this is a constant, just say it's like theta of 1 or whatever. But I'll have two parameters. I'll have c and I'll have delta, and I will say that the expected number of triangles involving only vertices of expected degree at most c is at least delta n. So this is sort of the property that I would like. I would like the expected number of triangles that involve only vertices of expected degree at most c, where c is a constant, to be at most delta n, where again delta is a constant. So think of delta and c being constants. And so the theorem is essentially that if v1 up to vn generate graphs with the above property. So I'm being a little loose with my language here. I just don't want to rewrite. What I mean is, suppose v1 and v1 up to vn had the property that this was true, that the expected number of triangles involving only vertices of expected degree at most c is at least delta n. So suppose this is true with this above property, then the rank of these is at least essentially it's something like the way to look at this is it's some polynomial in delta divided by c times n divided by log squared of n. Okay, this is what you get. So you get that the rank of these vertices, so that you can also think of d as the rank, right? Because these were so you could think of what this means is that the inherent dimension, these were vertices, these are vectors in d-dimensional space. I'll say that what this implies is basically that d is essentially greater than n over log squared n, where I treat the delta and c as constants. So this is the theorem that I want to prove, right? The d is going to be omega of n. I should probably put an omega over there. But this is the main theorem, and this is what we're going to prove. So any questions about that? Okay, so let me continue. Now I'm going to sort of show you the proof. So I'm going to start by basically sketching out the proof for a special case, which is actually of non-trivial interest. Okay, so let me start just to sort of warm ourselves up. Let's assume that the v1 up to vn are actually are all non-negative vectors. Furthermore, and for all I, let's assume that all these vertices have exactly the same length L. So these are all vertices that are non-negative and have exactly the same length. And this is actually not an unreasonable restriction to think about, because in many cases, people use vectors that are normalized. And so if all the vectors had unit length, meaning that the L was 1, these would be non-negative vectors, non-negative unit vectors. And if you have non-negative unit vectors, then essentially, the max and the min disappear, right? These two things disappear. And this is exactly the cosine similarity, right? So if this is cosine similarity, this is cosine similarity when the length is equal to 1, and of course these are non-negative and non-negative. So when you have non-negative vectors of length 1, then this is looking at cosine similarity, which is by itself sort of a very reasonable model that people would study. And interestingly, what happens in this case is actually you can improve the lower bound to just n. It's essentially saying that you need all the dimensions, of course, with this polynomial dependence on delta and c. Okay, so if that is clear, what I'll do is I will just I'll just give you a sketch of the proof. So let me start. Okay, so let me show you that essentially there is an inherent tension between two things here. One is the fact that you need the graph to have many vertices of low degree, whereas you need to have lots of triangles. Now the tension that is going to come up is that the fact that you need lots of triangles is going to force the length to go up. And the fact that you have many vertices of low degree is going to force the length to go down. And essentially there is no way of getting the right value of the length unless the rank is sufficiently high. So let me now sketch out the proof with this condition. So let me just use some notation. So given these vectors, and let me denote this as V. So I can think of V is essentially this D cross N matrix. So I'm going to think of this as V, and I will refer to this graph model as script G sub V. So script G sub V is a distribution of graphs on n vertices, where the distribution is described here. And so now let's just say, suppose G is generated from this distribution. What is the expected number of triangles in, and we can even keep it simpler. Well, let's just say that the expected number of triangles in the graph. Okay, so I'm just going to sort of write down an expression over here. And so this is going to be exactly the expectation. Now I'm summing over three different vertices I, j, and k of xij, xjk, and xki, where this is the indicator for ij being an edge. Right? So this is just an indicator random variable. So I'm just saying that if you look at any I, j, and k, the probability that ij, or rather the event that ij and k form a triangle, is the same as the event of all of these indicators being 1. Right? So if you have a triangle, then you need this edge to be present, you need this edge to be present, and this edge to be present. And what that means, quite simply, is that you have three edges, all three need to be present, so there is an indicator for each one of them, and that is what you get. Now, using linearity of expectation and the independence of ijk, and interestingly, all I need is just, I need only three-way independence. So, because I'm only looking at expectations, I can write this as I not equal to j not equal to k as the expectation of xij, the expectation of xjk, and the expectation of xki. Okay? Now, I've just said that, so, and let me, okay, so I'm going to fudge things a little bit over here just to make things clearer. But let's just write this out in this way. So what I can do is I'm going to assume, again, this is sort of without loss of generality. Just assume that all expected degrees are at most C. Remember, what I wanted was for the expected number of triangles involving only vertices of expected degree at most C, and this needs to be at most delta n. So what I can do is really I can look at these, I can throw away any vertex whose expected degree is more than C. So I'll only be left with vertices whose expected degree is at most C. So I throw away any high degree vertex. I will still have lots of triangles. So I'm sort of abusing notation here. What I mean by G is technically the induced subgraph on vertices of expected degree at most C. Okay, this is a technicality. In general, it doesn't really affect the proof, and it's just a lot easier to imagine that all vertices have constant degree. So you throw away the high degree vertices because you're interested only in the triangles that involve vertices which are all low degree. So now we come to this stage here, right? So this is linearity of expectation and independence. Linearity of expectation to switch the expectation in the sum, and independence to break the expectation of the product into a product of expectation. So this was independence here. Okay, so now I'm going to do something non-trivial here. I'm just going to say, suppose I look at the expectation of xij. Right? And what I know is that the expectation of xij, somewhat trivially, I can just bound this. Remember, it was basically at most, so it was at most a max of 0. So remember, it was basically this sort of, this was exactly equal to the max of 0, the min vi dot vj, comma 1. By Cauchy-Schwarz, the dot product, this is at most L square. This is Cauchy-Schwarz, right? This is Cauchy-Schwarz on this, and therefore I can actually just bound this by at most L squared, just by Cauchy-Schwarz. Remember, the length might even be less than 1, so we don't know. So if the length was more than 1, then this is a trivial bound. But when the length is small, this is a non-trivial bound. So I'm just going to bound the first term by Cauchy-Schwarz. And what I get is, I get the following. So I'm just going to bound this by L square. Then I get a summation over all I, and a summation over all j, and all k of the expectation of xjk and the expectation. So let me actually, I think it'll be convenient if what I'm going to do is I'm going to bound this term by L square. So I take this out there. So I get expectation of ik and then the expectation of ij. So what I did was I took this middle term, I bounded it by L square, moved it out. So now I have this triple summation here. So L square summation over all I, all j and k, the expectation of ik, and the expectation of ij. And the fact that these were unequal, I'm just upper bounding, so I'm going to assume they're all equal. This is not a problem. All right? Okay, so now I have my last bit of space over here. I'm going to say this is at most L square. So summation over I. Now this is, if you think about it, these two terms are basically identical, right? I'm summing over all k and all j. I'm summing over all vertices here. Which means that this and this, these are basically just, they're interchangeable, they're the same. What this really is I can say this is the summation, I'm just summing over all j of the expectation of xij. I'm getting the square of this over here. Okay? So hopefully this is clear. So what I did was I started with this expected number of triangles. I switched that. Then I get this product of expectations. I took the middle expectation, which is jk. I can take any one of them. I bound it by L squared. So that goes out there. Then I get a summation over I and a summation over jk. And then I get this term here. This I can just rewrite as that. So it's L squared, the summation over I, times the summation over j of xij. So fix I and look at the sum of expectations over all the other vertices and square that. Okay, so what is this quantity here? This is exactly the expected degree of the vertex. Right? This is exactly the expected degree of the vertex. So let me sort of move this and let me sort of show you what's going on there, right? So I'm just going to rewrite that expression down over here. I said the number of triangles in G is at most L squared times the summation of I times the expected degree of vertex I, that squared. Okay, so what I get is I bound the expected number of the triangles by, sorry, just a sec. Okay, the expected number of the triangles is at most L squared times the sum over I of the expected degree of vertex I. Now remember, this was at least delta times n. This is at most c. So what I get is delta n is less than L squared times cn, or that L is greater than equal to root delta over c. These are constants, so really you think of this as omega 1. So the punchline, the message here is that because the expected number of triangles is linear, you actually need all the length to be omega 1. That's the message. So all this calculation says is that the length is omega 1 when the expected number of triangles is at least delta n. Remember, I assume that all vertices are at most degree c. So any questions about this? Clear? Okay, so I guess, sorry, I probably fudged it. This should be c squared, and so I guess, yeah, there. That's what I should get, sorry. So it's L squared times c squared, right? The degree is c, so it's squared c squared, and this is what I got, root delta divided by c. This is omega 1. Okay. Okay, so now that I have this, so I know that all the lengths are large. I'm now going to sort of throw a theorem to bound the rank. So I want to bound, remember, so I have this matrix V, right? Which is the matrix of vectors. So this is n, this was d. What I'm going to do is actually I'm going to bound the rank of the gram matrix. So the Gramian, so the gram matrix of V is V transpose V. So V transpose V is an n cross n matrix. And the way to think of this matrix is that the ijth entry here is basically the dot product of the ith, sorry, let me just focus, is the dot product of the ith vector with the jth vector, right? The Gramian matrix is basically the matrix of pairwise dot products. So I'm going to bound the rank of this matrix, and I'm going to refer to this as M. So I'm going to call M as V transpose V. To bound the rank, I'm going to use this lemma. And the lemma basically says, so again, M is squared, right? So everything is, so it says that the rank of M is greater than equal to. So first what I do is I sum over all the diagonal entries and I square. So I take the sum of all the diagonal entries, I square it, divided by, now what I look at in the denominator is basically the Frobenius norm of the matrix. There. So this is the sum of the diagonal. So this is, it's essentially the trace of the matrix. So this is the trace squared divided by the Frobenius norm squared. So you can actually derive this inequality using Cauchy-Schwarz. Using Cauchy-Schwarz on basically the list of eigenvalues if they exist. In this case, they do exist. In general, even if the eigenvalues, you can use the singular values and you can derive this bound. Funny story about this is, the cleanest place where I've discovered this stated was in a blog post. And I discovered that blog post because I was actually reading through Terence Tao's blog on a related question on vector packing, and there was a comment. Down in the comments, there was someone who said, oh, there is a bound that also helps, and here's a link to my blog explaining it. So I clicked on that, and then sort of that's where we found this statement. Although it turns out that, for a gram matrix, this is fairly easy to derive by itself. So let's try to understand what this bound is saying. So again, here's my matrix now, right? Here's the n cross n matrix. So I'm looking at the trace. So those are all the diagonal entries. The Frobenius norm is summing over all entries. So this is the trace squared divided by Frobenius norm squared. What this is saying is if your diagonal entries tend to be extremely large, much larger than the off-diagonal entries, the rank must be high. Which kind of makes sense, right? If you look at the identity matrix, then essentially all the Frobenius norm is dominated by the diagonal entries. It's exactly the diagonal entries. What this is saying is even if it's approximately true, that the diagonal entries sort of contain most of the mass of the matrix, then that is enough to assert that the matrix has large rank. Why does this connect to triangles? Well, what is the diagonal entry of the Gramian matrix? It's exactly this. It's the 2 norm squared. Right? The diagonal entry is exactly the 2 norm squared. We assume that all the lengths were the same, and so this is exactly L squared. So the diagonal entry, these are all L squared. And we have a lower bound on L. We know that L is at least a constant, and this was because there are many triangles. So this is why the triangles are important. The triangles are important to show that the diagonal entries, which is the length, is large. So what does the numerator become? The numerator of this becomes n times L square, which is n square times L to the 4th. Again, let's just assume delta and C are constants. This just makes things easier to look at. So this is omega n squared. So this says that the numerator of the matrix is omega n squared. So now we need to bound the denominator of the matrix. Now one has to be a little careful here, right? The denominator of the matrix also involves the length, but it's not squared. The sum is, like, each individual length is squared, but the sum is not squared. So what we need to show is that the numerator we just showed is quadratic. We need to show that the denominator is linear. Okay? We need to show the denominator is linear. And here is where again the graph sparsity is going to play a role. So any questions about this point? Does this make sense? Okay. So let me continue here. Now I need to bound the denominator of the matrix. So I have a denominator, of this bound. So I'm looking essentially at I'm just looking at the Frobenius norm of the matrix. Now here's what I'm going to do. I'm going to say, well, I'm going to split this sum up into two parts. So I'm summing over all I and j, and I'm going to sum this over all, so I'll sum over all ij. Let me write this out this way. I'll sum over all ij such that, remember, and just let me, because we're talking about the gram matrix, mij is just vi dot vj. So I'm just going to refer to vi dot vj directly. So I'm going to sum this over all vi dot vj being less than 1 and all vi dot vj being greater than 1. So I simply split the Frobenius norm, which are the entries all over, the sums of squares of all entries, into two groups. Those that are less than 1, those that are more than 1. So what I get is, let me look at the first sum. Right? So because these are exactly the places where mij is less than 1, this is just the summation over all ij. I can clearly upper bound it by vi dot vj, just the absolute value, because these entries are all more than 1. Right, so I just bound it, and again, because this was actually non-negative vectors, it makes the calculations a lot easier. I don't even have to do absolute value, right? I can just do directly vi dot vj. There's no absolute value here because these are all non-negative vectors. So this is simply the sum of entries of the Gramian matrix. Now, where of course vi dot vj was less than 1. Right? This is the sum of entries of the Gramian matrix. But this vi dot vj is exactly the probability of an edge being present. That's the probability that the edge ij is present, and I'm summing over some subset of entries here. So this is at most the expected number of edges in the graph, and this is at most c times n. And because I assumed all the vertices had expected degree c. So this is at most c times n. Or maybe I should say it's 2cn up to a constant. So that takes care of the first term. But what about the second term? The second term seems problematic because you cannot do this upper bound here anymore. But then you observe something, given how the model is set up. If the dot product is 1, then the edge is guaranteed to be present. Right? So if vi dot vj is more than 1, then the edge ij must be present. So I'll say if vi dot vj is more than 1, then the edge ij is present. Right? So now what I get is I get the sum over all ij of vi dot vj being greater than 1. So I did a minor fudge here. So not a fudge, but let me actually keep the length lying around here. Okay. All right. So now vi dot vj is more than 1 of mij squared, and remember this was the summation of ij of vi dot vj being more than 1, and what was mij squared? That was just vi dot vj squared. Okay. Now again, let me use Cauchy-Schwarz over here. By Cauchy-Schwarz, this is summation over ij vi dot vj being greater than 1. This thing is at most L square, so I get L to the fourth. Okay, I get the same L to the fourth over here. This is important. And remember, I said that if vi dot vj is more than 1, the edge ij must be present. What this means is there cannot be many entries. The number of these entries is at most the number of edges. So this is going to be at most L to the fourth times the expected number of edges. Because if vi dot v then is present with probability 1, like that edge will always be present. And so this is going to be at most L to the fourth times the number of edges. Okay? So now let's plug all of this in to our rank bound. So we get the rank of V, which I'm going to write out as the rank of the Gramian matrix, is less than equal to n square L to the fourth divided by 2cn plus c times L to the fourth times n. And okay, so how did I get this? Let me sort of put it all together for you. Remember, the rank of the matrix is the trace square divided by Frobenius norm square. How do I get the trace? I know that every diagonal entry is exactly L square, right? This is because it's the length of the vector, and there are n such entries, so that's n L square. Squaring the whole thing, I get n square L to the fourth. Okay? That is the numerator of the matrix. The denominator, I split into two parts. I split into the entries that are less than 1, the entries that are more than 1. So let me look at all the entries that are less than 1. I can then replace I can just remove the square because all the entries are less than 1. Then I just get the summation, of vi dot vj, where vi vj is less than 1. This is at most the expected number of edges. So this is 2 times c times n. Now let me look at the second part. Now in the second part, vi dot vj is greater than 1, so I cannot apply this upper bound. On the other hand, I know that if vi dot vj is greater than 1, the edge ij has to be present because it's present with probability, it's present with the probability the min of the dot product comma 1, and which is going to be 1. So there cannot be many edges present. Indeed, the number of such entries is at most the expected number of edges. So now let me process this. Let me do this part. So I have the sum of mij squared. Vi dot vj was strictly greater than 1. So I can replace this by the dot product. I replaced it by the dot product. The dot product is at most L squared. Cauchy-Schwarz here. So that was Cauchy-Schwarz. And then I get a fourth power here because vi dot vj was at most L squared, the square of which is L to the fourth. Right? So I go summation of vi dot vj strictly greater than 1 of L to the fourth. But how many such entries can there be? At most the expected number of edges, because each such entry gives you an edge of the graph. And I get this. So it's L to the fourth times the expected number of edges, which is at most 2c L to the fourth n. Okay? So plugging this in, this is what I get. So if I move things around, I get n. So I'll get n divided by 2c times L to the fourth divided by L to the fourth plus 1. And this is what I get. Now note that if L to the fourth was extremely small, I wouldn't get any useful lower bound here. But remember, I proved because of the triangle condition, I got L was greater than root delta by C. So L is at least a constant. So I'll just sort of write this out as L is at least a constant. And therefore you can show that this is also at least a constant. It's just some calculus. Right? So L is at least root delta divided by C. So what you get is obviously this is at least a constant, and given that treating delta and C as constants, you get omega n as the lower bound here. And that is sort of the entire calculation when the vectors are non-negative and have the same length. Okay, so any questions about that? Like if there are no questions, then so let me take some questions in the last about 10 minutes or so. What I can do is I will show you how to do the calculation when the lengths are potentially different. Any questions?
Yeah, one question here.
Yeah.
So I'm wondering why you split into the two cases. Like in my opinion, you can just bound everything with the later one. I mean, all the inner product are bounded by L squared, right?
No. So the problem is if you just bounded all of them by L squared, there may be too many entries. Right? There could be potentially n squared non-zero entries in this matrix. So you cannot bound all of them by L to the L square. Or in this case L to the fourth, right? Because it's the entry squared. Does that make sense? Remember, I mean, if I use this inequality without that, suppose I just did this. So then I'm just doing summation of ij L to the fourth. This could potentially be n squared times L to the fourth. Because I sum over the pairs that are definitely giving me edges, I get such a bound. You need this other part if all the entries were actually tiny. Suppose all the entries were like maybe 1 over n or so. So there are n squared non-zero entries. You cannot upper bound each entry by L to the fourth. I mean, it would be too loose a bound.
Yeah, got it.
Yeah.
Thank you.
Any other questions?
One question. You said something about the connection to triangles before starting to prove the bound.
Mm-hmm.
Can you repeat that again?
Yeah. So sorry. Do you see this part? This part has nothing to do with triangles, like getting up to here.
Right.
This part only had to do something with sparsity. Now you need a lower bound on L to get any reasonable lower bound. Right? If you have no bound on L, then you won't get any lower bound. And to get a lower bound on L, you need the triangles. So the triangles gives you this lower bound.
Right, yeah, I got it.
Any other questions? Okay, so now let me show you how to do it for the general lengths. I will still stick with non-negative vectors. With negative vectors, there are some additional complications, and maybe I can, if I have a few minutes left, I can tell you about how those are dealt with. So now let's just say that maybe the lengths are not necessarily the same. So the idea is to use binning. So what I can do is, if you go back to this proof that I showed you, and let's go back to this proof, and suppose instead of L, what I actually gave you was all of them were theta of L. The proof will still go through up to some loss of constants, whatever constant is over there. So as long as all the vectors have roughly the same length, I'm done. So I can just try to bin. So what I could do is I could bin, which means create bins of vertices where the lengths of the vectors basically is in 2 to the I and 2 to the I plus 1. Right, so you can create these bins. And what you can typically, this is a common trick, is that by some sort of averaging, you lose a factor of the number of bins. Right, so we'll see that you could basically bin. So if you create like k bins, then in each bin you might have n over k vectors, not n vectors. And then when you do the rest of the argument, instead of n, you get an n divided by k. So you lose a factor of k. So if the number of bins is small, then you're fine. The k is not too bad. And you could imagine that you should get like log n many bins. Except you have a problem. Lengths are not necessarily same, and they're unbounded. So we don't even know what the lengths are. Maybe there are some vectors that are exponentially long, and you use that to potentially embed something. So to deal with this, first what we do is it's kind of somewhat, well, okay, it's what you have to do is you have to sort of argue that we can throw away vectors that are too small or too large. So you can argue that you can throw away vectors that are either too small or too large. So what about the vectors that are too small? Now, essentially, what you can argue is so let me. What you can argue is that there cannot be too many vectors that are too small, because okay. So let me write this down, and because we're doing logarithmic binning, all we need to say is that a small vector is something where vi is, I'll say, like less than 1 over n squared. So really tiny vectors. It's not obvious that you can throw away such vectors, because there could be some other vector whose length was n squared, in which case the dot product could potentially be a constant. And so this such a small vector could potentially form edges. And I'll say a large vector is, in this case, is one where this is maybe more than root n, so is something polynomial. Once we do this, if we can throw away the small vectors and the large vectors, then the binning is going to work, because when you bin in powers of 2, you'll only have logarithmically many bins. So how do you throw away the small vectors? What you do here is you use the triangles. So let's actually start, and for the large vectors, what we will do is we'll use the sparsity. So how are we going to use the sparsity? So actually first we'll throw away the large vectors, then we'll throw away the small vectors. Okay. So I'm going to actually use a lemma. So this is a packing lemma. Again, this was the proof of this is it's relatively simple. It was also found on Terence Tao's blog. So this this paper owes a lot of sort of cites a lot of credit to Terence Tao's blog posts. So it says consider any, and in this case I think you get like 2 times d unit vectors u1 up to u2d in r to the d. So these are unit vectors. Then there exists I not equal to j such that ui dot uj, I'm sorry, the absolute value of that is at least 1 over root d. So what this says, And yeah, so what this says is if you consider any 2D unit vectors, I think even you could even probably do D unit vectors, there must exist a pair of vectors whose dot product is at least 1 over root D. Okay? So this says, so hopefully this makes sense. It says if you have any collection of unit vectors, this is like a packing problem. You cannot have too many vectors such that all absolute values of dot products are close to 0, which kind of makes sense, right? You can put at most, I guess you cannot have this to be D, I'm sorry. So you cannot have D, this wouldn't work with D, because you could just take the D axis, the axis unit vectors, the axis parallel, vectors, basically the basis vectors, and all the dot products are 0. But if you take 2 times D vectors, then it makes sense that you cannot have all of them be 0, but could all of them be extremely small? And this gives a lower bound. It says that no, you actually have to have at least this. Okay? Okay, so now what this says is, now let's look at the long vectors, right? So let's just we can assume that the overall dimension is less than n, and I think one could probably even replace this by even with an n to the 1/4, then it would still work. So consider 2 large vectors, 2 large vectors. Right, so you have vi dot vj, and this is going to be at least, I'll say, yeah. So this is at least, I think, this will be at least, I can write this out as the length times this, the length of that. I'll say this is actually equal to the length of this times ui dot uj, where these are the normalized versions. Right? So this is exactly equal to just taking the lengths out and looking at the normalized versions. Now if these are large, so these are going to be at least root d, and if this is at least 1 over root d, then this is at least 1. So what this means is that if you have a collection of large vectors, they are going to essentially create edges with a relatively high likelihood over here. So let me sort of do this more formally. Let me do this more formally. So actually, you know what? I only have 3 minutes left, so maybe I'm not going to do it in too much formalism. And let me just say that the key property is to argue that if you have a lot of vectors that are of length more than root n, then because of this packing property, there will be many pairs of vectors whose dot products are going to be more than 1. Just because what this says is if you normalize them, then the dot product is going to be at least 1 over root d, which will then lead to the overall dot product being more than 1. So if you have lots of large vectors, then essentially you end up with lots of edges because of that. And so the sparsity will say you cannot have too many large vectors. It's a little more complicated. You have to take these and then you have to create some independent sets with vertices, and it's not a difficult calculation, but it's somewhat technical. So you can throw away all the large vectors. Once you throw away all the large vectors, you can also throw away all the small vectors, because small vectors won't form many triangles. And to see that calculation, it's exactly the same calculation we did in the beginning, where we kind of were able to throw away, we were able to bound the lengths. We said, you remember in the beginning, we said that the length must be at least c divided by, root c divided by delta. Right? This calculation over here, dealing with the triangles and the lengths, right? So this calculation here, which said that if the number of triangles is large, then you can lower bound L. So you can just do the same calculation except with those where L is tiny and argue that they cannot create many triangles. And if the small vectors cannot create many triangles, you can throw them away. So what this means is you end up with vertices. So you can kind of argue, essentially focus on VIs such that the length is basically between 1 over n squared and root n. And this will contain most of the triangles. So it says if you throw away the small vectors and throw away the large vectors, it will contain most of the triangles. And then you do some binning on top of this, and then you can essentially apply the argument where the lengths are the same, because in each bin, the lengths are roughly the same. So with that, let me end. And if you have any questions, I'll take questions now.